Okay, hey, welcome back. We're going to start integrating over surfaces. So just to recall what we've been doing, we first integrated over curves or on curves. So we saw the integral of ds, which is basically just going to be the arc length formula. And that would give us the length of the curve. Uh, so before, kind of, we had this guy. And now for surfaces, we have the double integral of s d big S. And of course, to evaluate this arc length thing, we would have to parameterize everything. You would end up with I believe, the integral of the square root of x prime of t squared plus y prime of t squared dt. And this thing right here, of course, is just the magnitude of r prime of t. But yeah, okay, we get it. Right, so now the formula that we're using, we kind of have to put this into terms, and this would have been it from a to b. We think of this as integrating over some region r of the square root of 1 plus the partial with respect to x squared plus a partial with respect to y squared times dA. But we also thought now in a parametric form where to evaluate that version, you would integrate over some region D in the UV plane, and the formula then in that case would be R with respect to U cross R with respect to V dA. Okay. Okay, so we didn't really start with this formula before. I don't think we started there exactly. I mean, we did kind of technically because we had seen the parametric form way back in Calc 2. At the end of Calc 2, they actually introduced that. But where we started before in section, was it 15.2, was actually integrating some function like f of xy over some curve, right? And then, of course, to evaluate that, we would maybe have to parameterize f of it would be x of t comma y of t, and then times the square root of x prime of t squared plus y prime of t squared dt from t equals whatever to whatever. So the only difference is basically we're tacking on this additional f of xy part right into here. So what we want to do then now is kind of the same idea. We want to tack on some function in here, okay, in the inside of these integrals. So now what we'll be doing is basically doing an integral over a surface, and visually it's no big deal. It'll just be plopping this function f of x y z into here. No big deal, right? And then to evaluate, we'll have to probably parameterize it, but first we would have to rewrite it as an integral over a region of f of x y z times the square root of 1 plus the partial with respect to x squared plus the partial with respect to y squared dA. Then in the parametric form, we'll also have to deal with that. So you would end up with some r of uv function plopped in here, ds. And then to evaluate that, of course, we have to convert everything over, and we can kind of start at the same place. Let's not put r of uv. Let's put f of x y z ds, and then we'll convert it over to our uv plane by doing substitution. So you'd have f of x of uv comma y of uv comma z of uv, and then this would be the magnitude of ru cross rv dA, which is du dv or dv du. Okay, so again, it's basically all we're doing in this section is integrating over a surface by kind of plopping in plopping in a function in our integrals. Okay, so I mean, I don't want to say visually because I don't want to mean geometrically. So, but this is kind of the idea. Okay, visually, what's happening is that we are kind of okay. So for the if we get a surface z equals f of x y, let's go to our I guess Twinkie in space. Oh gosh, I just ate something. Sorry, it's not agreeing with me. Something like this. And we're here. And of course, there's the projection of it into the XY plane here. And we're, chopping that up into a bunch of sections and then maybe considering one particular part of the surface. Maybe that part is the result of projecting this part onto the surface, or onto the plane rather. So what we're doing is kind of this guy, we're approximating that with the tangent plane, recall. So maybe this is kind of like this curled type plane, and then we're attaching tangent plane. So we'll approximate this surface, which we call change in s sub I, with this change in t sub I. But on top of that, we're going to also kind of attach some functional value. Okay, so f of x, y, z on top of it. So geometrically, what that is kind of the volume of a cube sticking out of it, right? Because it'll be basically the area of the little tangent plane times some f of x, y, z, which will give you basically the volume of that cube that's attached to the surface. So that's kind of what I mean by you're integrating over the surface, right? And let's see how so you're forming this new kind of increment. I guess I'll call it delta. I don't know what to call it at this point. Delta big Z sub I, which we'll say is f of x sub I comma y sub I comma z sub I times we wish the change in s sub I, but of course we're approximating change in s sub I with that crazy square root thing, and then we're summing across over the surface and getting our sort of integral as we take the limit as the norms of the rectangles in the xy plane go to 0. Okay, so we'll have the sum of these f of x sub I, y sub I, z sub I, change in s sub I, and as the limit of the norms goes to 0, you'll get the integral du jour, the double integral over the surface S of f of x, y, z. Okay, and what I'm saying is it's basically very similar to what you did before with an integral of a function over a curve in maybe like the xy plane. Right, so if you're here in the xy plane, you have some sort of curve, and maybe you can imagine attaching a function to it is kind of like figuring out the area of this of a wall that's built on top of the curve. Just like here, it's going to be a volume kind of scenario. But yeah, that's it. I mean, you're adding up this function over the surface. You can do whatever you want with it. You can do mass, figure out that sort of thing. Okay, so anyways, let's look at some of these problems. Okay, so without further ado, maybe we should look at some of the problems in the homework. So we'll do this, and then we'll also have to do the kind of the vector versions as well. Okay, so do recall that we also did that in the line integrals. We had the vector version. Okay, so also then and I'll remind you of this when we get there. We also looked at the integral of the vector field F on the curve C. Okay, and we'll have to develop some formulas for that as well in this new context. Okay, so anyways, the beginning problems, like number 2, we're figuring out the surface integral, the integral of x minus 8y plus z over the surface. It's the integral of x minus 8y plus z over the surface given by these formulas. Z equals 9y. Okay, and then we're restricting x and y to be from 0 to 2, and then for y it's from 0 to x. Okay, so z equals 9y, that's just a plane, and then we're integrating over let's see, 0 to 2, and then 0 to x is just this line. Okay, so we're integrating over this little triangle region. I'm not going to try to draw the surface, but we do need our partial derivatives. So z with respect to x is just 0, z with respect to y will be 9, and then we'll have the double integral of x minus 8y plus, and we have to rewrite z so we can do this double integral. Z is equal to 9y, so plus 9y, and then it'll be dy dx, and of course then y goes from the line y equals 0 to the line y equals x, so 0 to x, and then x is going from 0 to 2, and we should be able to just go at it then. Whoops, I forgot the square root part. Sorry about that. So got to tack that in as well. So you have the square root of 1 plus z sub x squared is 0 plus z sub y squared is 81 dy dx. And so you could factor out the square root of 82, and 8x minus 8y plus 9y is x plus y dy dx. So this will be square root of 82, double integral. Well, let's go ahead and integrate with respect to y. So we'd have xy plus y squared over 2 times dx, and we have to evaluate that from 0 to x. So we'll end up with square root of 82 times the integral of x times y is now x, so x squared plus x squared all over 2, and then minus 0. We can simplify that, so that's square root of 82 integral 2 halves plus 1 halves is 3 halves, so I'll have a 3 halves x squared dx. You can factor out the 3 halves, you get 3 square root 82 all over 2, and then I have to integrate x squared, so that's going to be x cubed all over 3 from 0 to 2. The 3's cancel. I'll have x cubed all over 2 from 0 to 2. And I still have a square root 82 floating about. And then 2 cubed is 8. 8 divided by 2 is 4. So I'm getting 4 square root 82. Okay. So pretty simple, so long as you don't forget. It's remembering all of it, you know, on a test. It's like, oh, I'm going to remember all this. Like I said, you could do applications with this. Find the mass of the surface of lambda s density rho. So basically for number 4, I'll just set it up, I won't do it. We're integrating over the surface given by this plane, 2x plus 3y plus 6z equals 12. And then we want to work with this character here, x squared plus y squared. And so my double integral will be of x squared plus y squared over this region. So I'm going to rewrite it. So 6z equals 12 minus 2x minus 3y divided by 6. 2 minus x over 3 minus y over 2. And then I need zx, which will be what? Negative 1/3, and then zy will be negative 1/2. So it'd be x squared plus y squared times the square root of 1 plus 1/9 plus 1/4, and then your dy dx. We need to get the projection of the surface into, I think it said the first octant. Yeah, so they want the mass of the surface lamina S of density rho in the first octant. So you're thinking the projection into the xy plane. Let z be 0. So if z is 0, you'll get 2x plus 3y equals 12. So you'll have 3y equals negative 2x plus 12. So you get y is negative 2/3 x plus 4. So in the first quadrant, it seems I am going from 0 to that thing, right? If I graphed it just in 3 dimensions, you could kind of see it. So I just want to make sure I'm not getting the wrong region. When x and y are 0, z is 2. When y and z are 0, x is 6. 2, 3, 4, 5, 6. And then when x and z are 0, y is 4. 1, 2, 3, 4. So that's our surface. And of course, in the first quadrant, it's just this triangle region that we're integrating over. So, sure, it'll be 1, 2, 3, 4, 5, 6, 0. And then on the y-axis, 1, 2, 3, 4. So it's this region. So I'm integrating from y equals 0 to y equals negative 2/3 x plus 4. And then x equals 0 to x equals, I said 6, right? So 0 to 6. This integral looks pretty nasty to me, believe it or not. It just looks like a freaking nightmare. I'd have to FOIL. It's not that bad. You just have to FOIL out, and that's going to be nasty with that fraction. So it won't be so bad. But you know, you can always check your answer before you submit by going to like Wolfram and then typing it in and making sure you get the right answer, right? So int of x squared plus y squared. And I honestly would not even put that square root junk in there. I just tack that on at the end. So x squared plus y squared, comma. Looks like I'm going y equals 0 to negative 2/3 x plus 4, comma, x equals 0 to 6. Push enter. This razzmatazz right here is going to be the square root of 36 plus 4 plus 9 all over 36, which is 49 over 36, which is 7/6 once you take the square root of it. So this answer should be 7/6 times 104, and whatever the heck that is, right? So 7/6 times 104 is, drumroll, 364/3. And let's make sure, yeah, okay. So, you know, if you want to, before you start, you can kind of see what it's going to be, and you'll know then if you made any mistakes in your work. Okay, so some of the integrals can be kind of nasty. Again, I don't want to bumble through one for you. I've already done that. You don't know if there's much to learn by seeing me make a mistake, right? So anyways, now we want to consider the other form in parametric, the parametric form. And again, all you're doing is kind of slapping in this function and you're integrating over it. So I kind of didn't even set up a section. I feel bad for that. So let's call this first section section 1, z equals f of xy, and we're doing surface integrals on that. Section 2, then we're moving into the parametric form. Okay, so the surface integral in this case will, again, f of x, y, z ds. So you're integrating that function on the surface, and then to integrate it, we're going to reparameterize everything in terms of u's and v's. And instead of that square root 1 plus fx squared plus fy squared, it'll be the magnitude of the cross product of RU and RV, dA, right? And we're integrating over some weird region in the UV plane. So let's see if we can get our hands on one of those. Sometimes you got to go polar, go convert the polar to evaluate some of these. We'll just try number 5. So I have the double integral of s of y plus 4 ds, and the region, or rather the surface, is going to be u comma v comma 5 v, and then the region we're integrating over in the UV plane is some box, right? 0 to 1 of the u-axis, and then 0 to v to 3 on the v-axis. So it's this box we're integrating over. Okay, so I need to get the partial derivatives and then their cross product to pull this off. RU will be 1, 0, 0. That should be painless. RV 0, 1, 5. And the cross product equals, cover up the first column, 0 minus 0. Cover up the second column, minus 5 minus 0. Cover up the third column, 1 minus 0. So this will be 0, negative 5, 1. I need the magnitude of that for my integral. So that's going to be square root of 25 plus 1, which is square root 26. Stuff it all into my integral now. So I'm integrating over this region D. I'm going to rewrite this u plus 4 now using our new parameterization. Y plus 4, I'll write that y is v. So I have v plus 4. And then times the square root of 26 times d, we'll go v and then du, right? So we'll do dv first, and of course the bounds on v, u the 0 to 3, the limits on the inner integral is 0 to 3, and then the outer one 0 to 1. So I can factor out the 26, and I'll have v squared over 2 plus 4v du. And then I'll have square root 26 integral of, did I just integrate that? Oh, I didn't mean to integrate that already. Okay, so I integrated. I just have to evaluate on 0 to 3. So I have then, putting in 3, 9 halves, plus 12, which is really 24 halves, du. That will be 33 halves times the square root of 26 times the integral from 0 to 1 of du, which of course will just be u evaluated from 0 to 1 will be 1. So I'll just have 33 halves times the square root of 26, which is the right answer. Okay. So now we want to we have basically, we're doing integrals of a function over a surface. Okay. In 15.2 we did integrals of a function on a curve, but we also did integrals of a vector field on a curve. So now we want to do an integral of a vector field on a surface. right? So first things first, we need to kind of define just what exactly we're after. Um, and in order to pull this off, we're going to have to talk about orientation. When we dealt with our, so let's make this section, I think it's 1, 2, 3 now. And we're dealing with vector field, surface integrals on vector, surface integrals, which are basically integrals of vector fields on surfaces. Okay, so the book will call this the vector version or the vector form of the surface integral. So again, before, what we do, we had the integral of f dot dr, and if you remember when we first initially introduced it, it was really the alignment between the vector in the force field and the tangent vector to the curve. Okay, and then dt, and of course we could rewrite the tangent vector as r prime of t divided by the magnitude of r prime of t dt, and then we were able to kind of do some fancy footwork and rewrite it, noting that ds, if you think about first the arc length, s equals the integral of the magnitude of r prime of t dt, then we could take the derivative of that with respect to t, and you just get the magnitude of r prime of t, right? So ds then, ds would then be the magnitude of r prime of t dt, and so I'm missing something. This would be ds right here. Okay, ds like that, sorry, and then this would be ds. Okay, so plopping this in to here gave us then the integral of f dotted with r prime of t times or all over the magnitude of r prime of t which you could rethink of as 1 all over ds dt. Okay, so this object here in the denominator, if you were to solve, I mean, it's this thing right here, right? So you could replace it with ds over dt, and you would have the integral of f dotted with r prime of t, multiplying by reciprocal, you get dt all over ds, the ds's cancel, and you have the integral of f dotted with r prime of t. R prime of t is just the derivative of r with respect to t times dt, and then the dt's canceled, and we had that form that we were introduced to for the vector version of the line integral. But I guess my long story short, the point was when we introduced it, it was this integral, which represented kind of the sum of the alignment between the force vector and the tangent vector over the curve. So what did that represent? We had some sort of curve, and it could be in space, right? So that was where I did kind of a weird, you can get as crazy as you want with these curves, I guess, to a certain extent, probably. Kind of make it go down like that. Whoops. Let's make it look a little prettier. Maybe it goes in like this, and then goes over like this, and maybe comes back up and goes down, and maybe comes over here and starts going around. I don't know. butchering it, but you get the idea, right? So what we're doing is basically cutting this curve up into a bunch of ds segments, or delta s arc length segments, and then we're considering the alignment between the tangent vector and the force field vector. So in this space, there exists a vector at every point. So in particular, at that one point on the curve, there's going to be a force field vector. Maybe put it in yellow. And what that integral is doing, because it's a dot product, this f dot t represents kind of the alignment between these two vectors. Because remember, f dot t is equal to the magnitude of f times the magnitude of t times cosine theta. So the more aligned they are, the bigger that f dot t is going to be. And our integral is basically just adding up all of these f dot t things times the line segment length. And then when we take the limit as the line segment length goes to 0, we ended up with our vector version for the line integral. Okay. So long story short, we kind of want to do the same thing, but on a surface. So how is that going to relate now to this new picture that we're dealing with? So now you can take your favorite surface. We've been using the Twinkie, maybe the front of a shoe, some sort of surface like this. And what we're going to do is immerse this in a force field as usual. And then at some point on the surface, there will be a tangent plane to it. And we can consider then the alignment kind of between the normal vector on that tangent plane. So maybe this vector is the normal vector, and then the force field vector. Okay. So everywhere in space there's going to be a force vector. We're going to add up all of those and then multiply them by the area of that little tangent plane, right? So we're going to get a bunch of these, and the book has a nice little picture somewhere. Yeah, a bunch of these kind of rectangular pictures. They're going to call it delta V, which will be a dot product between f and n, which kind of represents the height of a cube or some weird parallelepiped object, and then times the area of that base, okay, which will be delta s. From this, we're going to produce our new formula, and in order to produce that formula, the hard part is this normal vector. We need to get a formula for that. We'll have a formula for everything else. You know, it's going to be the sum of all these delta v's, and then you take the limit as the norm in the projection of the little rectangle that this thing is over top of. We want the norm of that thing to go to 0, and we'll end up with the double integral over the surface of f dotted with n ds. Okay, so ultimately that will be the kind of the thing that we want to work with, and that will be called the flux integral. You can think of it as kind of, if this surface represented maybe like a membrane, the flux integral will measure how much fluid would be going through that membrane, okay? Where the force field would be representing kind of a fluid and moving across some sort of membrane. So you can imagine biology people being very interested in this sort of thing, okay? I had a chemist once who was, for some reason, interested in containing fluids in bags, and he would need to know sort of how much fluid would, so it was a bunch of layers of bags, and he needed to figure out the fluid flow between each layer of bag for some weird thing he was doing as a chemist. So it comes up. Okay, so I need to develop a formula for this normal vector, and I need to do it in two ways, because now we have the surface z equals f of xy, but also the surface r of uv. All right, so you need two different versions of normal vectors. So let's set it up. Part A, we're talking about orientation, basically, of the surface. And what we mean by orientation is we could put these normal vectors on the top of the surface, like we have here, but if you think about inside of the surface, there's going to be a normal vector pointing down, right? So we have to pick which one we want, and therefore we're going to have like two formulas. Okay. In the homework, you're always going to be using the outward pointing normal vector, so it won't really be too painful for us, but there are a lot of formulas to deal with. Okay, so orientation of surface, part 1, we want to deal with z equals, and the book is going to call it g of xy. And the first thing you got to do, just like what we did when we were building tangent planes for these surfaces, is to rewrite your equation as z minus g of xy, and then give that a new name, big G of xyz. Okay, and then the normal vector there will just be the gradient. Okay, so the normal vector, but we want a unit normal vector, right? So it's a gradient, sure, but then you have to divide by the magnitude of the gradient. So gradient of g of x, y, z, all over the magnitude of that thing, and that will be the upward unit normal vector. And then downwards is just the negative of that. Okay. But like I said in the homework, we're always going to be using the upward unit normal vector, so don't even worry about it. Okay. So that's the z version. Then the parametric version. Of course, you're just doing cross products of partial derivatives, then dividing by the magnitude again. So it's just be, for the normal, it's the cross product of RU cross RV, cross product all over the magnitude. Again, unit normal vector. Okay, so all over the magnitude of RU cross RV, or this would be up, or the down version is just the reverse cross product, RV cross RU. Okay, so it's never an issue where you kind of have to plot it. At least it's usually not an issue where you have to plot the thing and kind of look where is it oriented out or where is it oriented down. Usually up. Okay, usually. All right, so there's those two formulas. Now we want to build the surface integrals of the vector fields over surfaces. So using these things then, in part B, we will be able to produce the flux integrals. And basically it's just these integrals I was talking about here, where we're kind of measuring at on each rectangle the amount of flow or the amount of alignment between the normal vector and the force field vector at that particular tangent plane. And it's just that integral that I have here. Okay, so we want to flesh it out a bit. So the first version, then the z equals g of xy version, you have the double integral of f dotted with n. That's going to be this thing, though, the gradient of g over the magnitude of the gradient of g, times this square root of 1 plus fx squared plus fy squared, and then dA, right? But if you think about it, the magnitude of the gradient there is just the 1 plus fx squared plus fy squared, okay? Because your gradient of this thing here, the z component, is 1, and then you got partial derivatives of g with respect to x, g with respect to y. It's going to cause a cancellation between those two objects, and so what you're going to end up with is basically just the double integral of f dotted with the gradient of g dA. Okay, so let's make sure, yeah, so you can see the cancellations here as they kind of flesh it out, and then they really write it out in terms of all the little components if you were to substitute in the components. Okay, so the gradient of g in this case, just by the way, is going to be equal to negative g with respect to x, comma, negative g with respect to y, and then 1. Okay, where did I get that? It's from just taking the gradient of that thing and plugging in the components. Okay, and this is the upward version. All right, so 2, then we got r of uv, and we want to play the same game. So now we have f dotted with the cross products. So in the numerator, it's just a normal cross product. In the denominator, it's the magnitude of the cross product. So you have RU cross RV all over magnitude of that thing. But then ds, if you remember, what the heck is that? ds is really just the magnitude of RU cross RV times dA. So again, you get this nice little cancellation, and what you're looking at then is the integral of the dot product between the force field and this other thing, which will also be a vector. Okay, RU cross RV. And then you'll parameterize the force field in terms of u's and v's, and you'll have your full picture. Okay. Like I was saying in the homework, you're mainly going to be dealing with the upward unit normal vector, or see problem 7. Upward unit normal, upward unit normal, it's always upward unit normal. So you're not going to have to worry about, at least for now, the other versions. Some points later, when we're trying to prove like Stokes' theorem, or trying to establish Stokes and the divergence theorem, you may have to worry about orientation as you go around and integrate over surfaces. But for now, it's not an issue. So anyways, let's